Hi, my name is Oliver Knitter. I'm an applied mathematician and a quantum computing postdoctoral researcher at SandboxAQ. And I wanted to take this opportunity to tell you all about some cool research that we're working on related to machine learning and quantum computing and quantum chemistry. One interesting but kind of frustrating thing at times about AI for science and related research is how interdisciplinary it all is. Anyone who wants to work in this field often enters it with a lot of background knowledge that they have to offer, but also a lot of additional related knowledge that they might need to get up to speed on. And so our hope for this kind of video is whether you are an enthusiast or a researcher in the field, hopefully there's something in here that you all can take away. In particular, what I'd like to show you all today is this new paper that we have out that was just accepted for publication on an interesting field called neural quantum states, which is a classical deep learning method that, in a sense, mimics a lot of the kind of behavior that we would like to see from quantum computers. And we're specifically using this method to try to solve some fundamental problems in quantum chemistry. Quantum chemistry is a very exciting field that a lot of people in this general area are looking at now, and our hope is that neural quantum states, or NQS as we often call it, can eventually help us find a new method to solve some of these problems that scales very, very well as the problem size grows without losing accuracy. Maintaining this balance is a bit of a tricky thing in ordinary computational chemistry calculations, and we're hoping that this new field can have something to offer there. So the first thing we should talk about is, well, what is quantum chemistry? It sounds pretty cool, but what exactly does it entail? Essentially, quantum chemistry studies the quantum mechanical behavior of individual molecules and chemical compounds, using the methods of quantum mechanics to help us understand how these molecules are structured and how they behave as they interact with each other. Truthfully, a lot of quantum chemistry really just breaks down to understanding where, in a quantum sense, the electrons of the molecule are around the molecule itself. Electrons are something that we often, learn about in school as like planets orbiting a sun. If you look at an atom, the nucleus, we visualize it as sitting in the middle of the atom, and the electrons circle around it in orbits. But we've known for about 100 years now that that's not exactly what electrons do. Electrons are quantum particles. We can't exactly think of them as specific, spherical objects spinning around in space. Instead of orbiting the atoms, what electrons do is they essentially vibrate in standing waves around the atom. And this vibration is based on the principles of quantum mechanics. Now, when we're looking at an atom or a molecule, all of the electrons in this system inhabit certain regions of space called orbitals. I'll get into that a little bit more later, but essentially the orbitals help us understand where around the molecule the electrons might be. Now, one thing we have to keep in mind here is that technically all of the particles inside a molecule are quantum particles. The electrons are quantum, the nuclei are quantum because each one consists of protons and neutrons just clumped together, so those are all quantum particles. But if we considered all of these individual particles together, the quantum mechanical system we'd have to understand would be humongous relative to the number of particles we have. And so for these quantum chemistry calculations, we often use what we call the Born-Oppenheimer principle. This was first developed about 100 years ago by the quantum physicist Max Born and his then graduate student J. Robert Oppenheimer. Now, what the Born-Oppenheimer approximation essentially says is that technically atomic nuclei are quantum, but they're so much more massive and so much slower than electrons. And so instead of considering the entire molecule as one big quantum system, we think of the nuclei inside the molecule as fixed electrically charged points in space, and we only consider the quantum behavior of the electrons as they move around these atomic nuclei. Now, this behavior is determined by a mathematical operator that we call the Hamiltonian. This essentially captures all of the energy that's inside the molecule, the kinetic energy from the movement of the electrons, and the potential energy, how the electric charges of the electrons interact with each other and with the nuclei of the molecule. Now, this is where the orbitals come back into play. Without thinking about the orbitals, we, for all we know, would have to look at any region of space around the nuclei where the electrons could be. But orbitals are specific regions of space that split up the space around the molecule into distinct dimensions. These aren't physical dimensions, but these are mathematical dimensions. And when we measure the positions of the electrons around the molecule, we will find that the electrons inhabit specific orbitals. And it's this exact behavior that helps us ground the calculations into something we can better understand. Anytime we measure where the electrons are around a molecule, we will find that they'll occupy certain orbitals. Some orbitals will have electrons in them, other orbitals will be completely empty. But in general, electrons don't specifically occupy certain orbitals. They exist in a quantum superposition of orbital occupancies. And the laws of quantum mechanics tell us that whenever we perform this measurement, our superposition collapses into a specific occupancy configuration of individual orbitals. Now, what we can do is we can take what we call a variational ansatze. This is essentially a trial wave function that we can control a little bit and tune to represent different quantum states. We can take this ansatze and optimize it against our Hamiltonian to try to find the quantum state that best approximates the true ground state of the electrons around our molecule. Now, the next question you might have is, what exactly do we use as a trial wave function? Like, what is that? What is that made of? And this brings us to the specific area of research that we're talking about today, which is neural quantum states. Neural quantum states is the application of classical deep neural networks as variational ansätze in these quantum problems. There are a couple of reasons why we would want to use deep neural networks for this. For however many orbitals you have describing your molecular system, the size of the quantum state space that your electrons could, inhabit is going to grow exponentially large with respect to the orbital number. And so understanding the full quantum state vector, as just a list of numbers describing every single entry in the state vector is prohibitively costly to do. It eventually the state vector becomes too large to even write down or store in a computer, even for molecules that aren't that big. So what we can use the neural network for is to encode all of this state vector information implicitly. We don't actually have to look at the entire state vector at once. We just use the neural network to store all of these entries, and whatever entries we want, we query the neural network to give it to us as output. Now, that takes care of storing the state vector, but it doesn't exactly answer how this process can be used to find the actual ground state energy. What we do to overcome this barrier is we use Monte Carlo sampling. What I mean by that is that every state vector in a quantum system corresponds with a specific probability distribution. This is the probability distribution that governs the wave function collapse we see whenever we actually measure which orbitals contain electrons and which ones don't. And what we can do is we can sample specific orbital configurations from this probability distribution and use that to reconstruct a proxy, a stochastic proxy of our true Hamiltonian energy, and perform some standard machine learning type optimizations against that approximation. And this allows us to navigate our entire quantum space without having to store or operate on any exponentially large pieces of information at once. Now, technically, neural quantum states is a general many-body quantum solver. It's a general solver for quantum problems, but it has shown a lot of recent promise in these electronic ground state calculations. So NQS describes a general machine learning paradigm. It doesn't really say anything specific about what types of neural networks we can use as trial wave functions. So a lot of recent research has been looking at different model architectures that might be helpful for these kinds of problems. In particular, a lot of recent development has been done using transformers, which are the backbone of large language models and much of the generative AI we see today, as the backbone of NQS ansätze. Now, I want to talk a little bit about transformers and how they operate and what they mean for this AI for science quantum chemistry context. Transformers operate on sequences of input tokens. In something like natural language processing, in LLMs, these tokens represent words from a language. But in NQS, what they instead represent are occupancy states of a molecular orbital. Does this orbital have an electron in it? Does it not? We feed these tokens into a transformer piece by piece, and once all of these tokens are inside the transformer itself will compare them all against each other and use these comparisons to generate some kind of answer. In the case of NQS, this answer is a state vector entry from the trial wave function that we're using the neural network to encode. Now, these transformer-based models have been shown to be very accurate, but we want to find some ways to improve their scalability without sacrificing this accuracy that we have. Transformers are so powerful because they explicitly compare all input tokens against each other inside what we call the attention mechanism. And this results in suboptimal computational scaling as the number of input tokens we feed into the transformer grows. Remember, each of these input tokens in the context of NQS represents a different molecular orbital. So as the size of your molecule grows, as the number of orbitals in your system grows, the number of tokens you have to place into the transformer grows as well. And this scaling is what we call quadratic with respect to the number of tokens in your transformer sequence. And this has led to a lot of recent efforts in NLP to try to find alternative architectures, specifically looking at recurrent neural networks, or RNNs, which used to be a popular tool for natural language processing, but fell out of favor for trainability purposes. Within the context of NLP, a lot of new RNNs have been developed that train in a more parallelizable format like transformers do. These are RNNs that train much more easily than old RNNs did, but that have better scaling properties than transformers because they are fundamentally leaner architectures. And one of these new methods is called the Retentive Network, or RetNet. Now, RetNets are RNNs that are very similar to transformers, but they replace attention with a new module that the developers of the RetNet call retention. Retention is a recurrent component that compares new input tokens in a sequence with a mathematical amalgamation of all the previous input tokens that the RetNet has seen. This is a recurrent module, but it can collapse into a parallelizable equivalent form, making RetNets as easy to train as transformers. So we're not completely avoiding this transformer quadratic scaling issue, but we're minimizing its impact as much as we possibly can. which is something that couldn't be done if we just used transformers instead. So what we did in our paper was we took an existing transformer-based NQS ansatz and wanted to see what happened if we just replaced the transformer with a RetNet component. In order to better understand how this replacement might affect NQS in a theoretical sense, we had to perform what we call a scaling analysis of the RetNet against the transformer. Within the context of LLMs, a scaling analysis like this typically extrapolates the total compute cost needed from a floating point operation or flop count estimate of what it would take computationally for a single transformer or transformer adjacent piece operating on a single input token for one forward pass. And everything else is just expanded and extrapolated from that point. So what we can do is we can do that sort of analysis separately for the parallel and recurrent forms of the RetNet. Parallel RetNets are essentially analogous to transformers and therefore have essentially the same computational cost. We do have to keep in mind, though, that RetNets are a little bigger than transformers are, so the absolute value of the cost is a little larger, but the scaling properties of the cost are essentially the same. Remember, transformers, and therefore parallel RetNets, have quadratic scaling with respect to the length of your input sequence, the number of input tokens you have. But recurrent RetNets, on the other hand, have only linear scaling. The dependency of the input sequence length on your compute cost is much, much weaker for the recurrent RetNet than it is for the parallel RetNet. Instead, the main determining factor of the compute cost for a recurrent RetNet comes from the dimension, the internal hidden state dimension inside the RetNet itself. The hidden state dimension of a RetNet is something that is generally influenced by the size of your problem, but is an entirely separate parameter than the problem size itself. And so what we can do is we can perform a direct comparison between the transformer compute requirements and the RetNet compute requirements for a specific problem size and a specific model size. What we find when we do a comparison like this is that there exists a specific ratio of problem size to model size, past which the RetNet is more computationally favorable. I want to reiterate, this isn't a question of problem size alone, but specifically of how large your model is relative to your problem size. If your model is too large, relatively speaking, then it's more favorable to use the transformer, even though technically transformers have worse scaling. But if your problem size is much, much larger than your model size, then it becomes favorable to use the RetNet. Interestingly enough, this ratio seems to indicate that RetNets may not be that great a replacement in existing LLMs. This is something that's slowly changing, but generally LLMs have internal dimension sizes that are quite large relative to the lengths of the sequences they operate on. And so RetNets may or may not be a suitable alternative to transformers within NLP. But NQS is a different scenario, and RetNets may be more amenable there. Now, because transformers are more complicated architectures than RNNs, technically they are more expressive, which means that we might find that a transformer will give us a better accuracy than a RetNet or other RNN would. And so one thing we incorporated into our workflow to help boost the overall accuracy of our model is an established technique that we call Variational Neural Annealing, or VNA. VNA was first developed in a different context for NQS problems, but hasn't really been tried on molecular Hamiltonians before. Essentially, VNA regularizes the Hamiltonian by a component that encourages wavefunctions to learn a more uniform state vector distribution. Remember, every state vector encoded by the wave function corresponds with a distribution over the quantum space. And so at the start of training, this regularization term will heavily encourage the model to learn a very uniform distribution, even if the true solution isn't all that uniform. And over the course of training, this regularization term is slowly annealed away. It affects the loss function less and less. And so what we hope this accomplishes is that at first our wave function is encouraged to learn a very uniform distribution, and over the course of training, very gently, our wave function will move from that uniform distribution to a more accurate distribution reflecting the solution of the problem that we want to solve. And what we've found is that the introduction alone of VNA heavily improves the accuracy of our model, even if we keep all other hyperparameters of our training setup the same. And in particular, this allows us to reach levels of accuracy using smaller neural network models, smaller model sizes, than what had been previously used in this field before, which is an interesting potential step towards improving the scalability of these models. We also tried applying VNA to older NQS models, besides the transformer and the RetNet, in particular one specific autoregressive model based on this masked MLP architecture called MADE. And what we found was that the introduction alone of VNA in this case heavily improved the accuracy of the MADE ansatz, in some cases beyond levels of accuracy that were previously known in the literature, which points to VNA as a very strong general technique for improving NQS within the context of quantum chemistry. Ultimately, for any quantum chemistry solver, accuracy is the most important thing to achieve, but scalability is right there behind accuracy as well. And what we're hoping this paper helps show is that it might be worth revisiting RNNs as NQS wave functions in order to help improve the scalability of NQS specifically for quantum chemistry calculations. Now, we have shown this with RetNets, which are very similar to transformers in a lot of ways. So it's not yet clear at this point whether or not RetNets specifically are the best RNN architecture to use in this context, or if a different type of RNN that's less similar might be even more beneficial. But new RNN architectures and new parallelizable RNNs are being developed every day. But either way, these new parallelizable architectures might make RNNs worth revisiting in general machine learning and AI for science applications. If anyone is interested in checking out some of these models for themselves, we have re-released an existing NQS open source codebase under the SandboxAQ GitHub repository called Tangelo Examples. Well, that's it for now. Thank you all for watching. I hope you enjoyed this video, and please be sure to check out some of our other content on the SandboxAQ YouTube channel.